Alright guys, I wanted to give us some extra practice using the washer and disk method, but specifically just defining the radius and setting up the integrals, because I think that's probably one of the trickiest parts. The integrals themselves are pretty easy to do. Usually it's just setting them up. And then within that, it's really just finding out what the radius or the radii are, depending on what method we're using. So again, I just wanted to, I gave us a little diagram here, and just wanted to practice setting up these integrals in hopes that that might help you with any of these problems going forward. So first thing I want to do is on part A is make a correction. Region R rotate around y equals 4 before I forget. That should be y equals 3. But anyways, let's review. It says in the diagram above, region R is contained between the semicircle, which we'll just call f of x, and the line y equals 3. The points of intersection are 2, 3, and 5, 3. Set up the integrals, but do not solve for the following volumes. So again, the area that's contained, right, is that region, okay, in there. All right, and what they're asking us for is to just set up, I'm gonna erase that, set up some integrals finding the volumes, okay, volumes through rotation. So the first one, part A, is region R rotated around y equals 3, not 4, y equals 3, so make that correction. So we're rotating it around this line y equals 3, which again would be that line right there. So when you think about rotating that around the line y equals 3, first question you should be thinking about, is it going to be a donut or is it going to be a disk method problem? Again, we talked before break that we can tell it's going to be a disk method because the entirety of that area we're rotating, okay, is touching that line y equals 3. Okay, so there are no gaps. Okay, so that's touching y equals 3. So if you think about actually rotating it, all right, you're going to be coming down here, and you're going to be getting kind of like this sphere, kind of just rotating around. Okay, which means its cross sections, okay, or its slices are going to be a disk. So if you remember in that case, all right, our formula, our general formula for disk, okay, was pi times sum bounds a to b, okay, of r squared dr, right? We had to identify what that radius was. So let's think about this. I'm just going to erase what I have here. What would the radius of this figure be? Okay, what is, or how would I express the distance from here to here, or any point on the line y equals 3 to the circle? What would that radius be in general? Well, the bounds, okay, hopefully you would see would be 2 to 5, so we would say that it would be pi times the integral from 2 to 5 of the radius. The radius is just, it's not simply f of x. F of x, technically, is the distance from, right, here all the way down to the x-axis. But I only want the distance from g of x, or sorry, f of x to the line y equals 3. So to express the radius, I really just should be saying f of x minus 3 squared dx. Okay, that would give me the volume of region R. All right, so pi times the region from 2 to 5, but it bounds 2 to 5 of f of x minus 3 squared dx. So be careful for those, okay? Be careful for those. All right, now it gets a little harder. Region R rotated around the x-axis. All right, rotated around the x-axis. So the first thing you should be thinking about, if you're rotating that shape, okay, around the x-axis, is it going to be a donut or is it going to be a disk? That is going to be a donut because the entirety of that region is not touching the x-axis. In fact, none of that region is touching the x-axis. None of this region here, right, is touching the x-axis. So when you rotate that around, you're going to have this big gap, okay, here, that the shape is not touching. So you're going to have like basically a donut, okay, a donut cross section. So, okay, when you think about donuts, the thing you should be thinking about is outer radius minus inner radius. So what we're looking for, what we really need to define, okay, we want to take the volume of this shape, okay, f of x, and we want to subtract from it the volume of the line y equals 3. So here's what we're going to do. We're going to be thinking outer radius minus inner radius. So again, how would you define? I would consider that the outer radius. And the way you can always tell what the outer radius and the inner radius is I would start at the line of axis of rotation, okay, and draw a line, okay, from the axis of rotation, okay, all the way to the furthest function, which in this case is f of x. And then I also want you to draw a line from the axis of rotation to the function, okay, the shorter of the two functions, which in this case is 3, so your inner radius. So in this case, we need to do pi. Sorry, let's talk about in general, outer radius minus inner radius. Your area is going to be pi, or your volume, sorry, is going to be pi a to b of your outer radius squared minus your inner radius squared, dr, whatever it may be in that case, okay? So in this case, we're going to be pi times, or from the bounds 2 to 5, of your outer radius, which in this case is f of x, but notice this is f of x squared, minus the inner radius squared, which is 3, so minus 3 squared dx. Okay, so what we're really doing is subtracting the volume of the outer shape minus the volume of the outer bounds minus the volume of the inner bounds. Okay, and again, the slice would look very much like a donut. All right, let's try C. Okay, C. Region R rotated around the line y equals 5. So again, since none of the region in this case is touching that axis, we know it's going to be a donut. So I know I'm going to be pi from the region 2 to 5. Now I need to find my outer radius. So if I go by my outer radius, again, I defined it as going from my axis of rotation to the furthest function, which in this case is a line y equals 3. So what's that outer radius there? Or i.e., what's the distance between 5 and 3? Well, you would find it by just doing 5 minus 3. So my outer radius is always going to be 5 minus 3, or 2, and then squared. And then we're going to subtract from it my inner radius, which is going to be from my axis of rotation, 5, to the function f of x. So how would you define that distance there? From here to here, there to there, there to there. It's always going to be 5 minus f of x. And then we don't forget to square it. I'm running over into part D here. Okay, but again, let's not forget what I'm defining here. I'm defining my outer radius minus my inner radius. And again, the way you can really check what that outer and inner radius are is to draw a line from the axis of rotation to the function itself, okay, to the outermost function and the innermost function. All right, try D. Try D on your own. I'll walk through D in a second, but maybe hit pause, try D, and see what you get. All right, so hopefully you gave it a shot. Let's walk through this. Since we are rotating it around the line y equals -2, and that the region R is never touching the line y equals -2, this is going to be a donut. So I know I'm going to be pi. My bounds are still going to be 2 to 5. Okay, I need to define my outer radius. Let's switch it up to yellow. My outer radius is going to be the longest of the two lines from the axis of rotation to the two functions. So if I just draw this up all the way, seems like my outer one is f of x, my inner one is 3. So my outer axis, or outer radius, is going to be f of x minus -2. F of x minus -2 squared. That's my outer radius. minus my inner radius, which is going to be 3 minus negative 2, which would be 5, but I'm just going to leave it as 3 minus negative 2 squared dx. Okay, so your outer radius squared minus your inner radius squared. Again, the hardest part is determining what the outer and inner radius are, but once you do that, it's much simpler. Okay. All right, if you flip over to the back, okay, we have this other problem. I want you to try this on your own. I'll walk through, I'll read it through the setup, and then I want you to pause it and try these two on your own, and then match, and then hit on pause and see if your answers match what I get. So let's read it first. So it says, in the diagram above, region M, okay, is contained between the graph y equals ln of x, oh great, the line x equals 5, and the x-axis. So here is our region that we're rotating. The points of intersection, I was very nice to you. I gave you the points of intersection 1, 0, and 5, 1.609. So there's that 5, 1.609 up there. Set up the integrals, but do not solve for the following volumes. Region M, rotated around the x-axis. Think about it as that donut or disk, and then go from there. And then region M, rotated around the line x equals negative 1. Again, think of that as donut or disk. And also, since we're rotating it vertically, or around a vertical line, think about, can you just use the function y equals ln of x, or do you need to change it into x equals something? The fact that I even mentioned that to you probably tells you what you should do, but just think about that. So try working through those two. Hit pause, and then hit play once you have answers, and I'll walk you through my answers. Okay, let me first erase the region so I can be a little clearer. All right, so we're rotating region M around the x-axis. That region is touching the axis of rotation the entire time. So I know this is going to be disk. So since we're rotating it horizontally, it's just going to be pi from 1 to 5. The radius is as simple, okay, as the height of the function. Again, if you go from the axis of rotation to the function, that's just going to be ln of x, so it's going to be just ln of x squared dx. Hopefully you got that one. That's probably on the easier side of things. Okay, but it's just pi times the integral from 1 to 5 of ln of x squared dx. This one's a little bit harder one. Part B, region M rotated around the line x equals negative 1. All right, so let's think about this. That region is being rotated around the line x equals negative 1. None of the region is touching the axis of rotation, so this must be a donut. So if it's a donut, then we need to identify what's the outer radius and what's the inner radius. So we're going to identify that by drawing a line from my axis of rotation all the way up to the first function, or the farthest function, which in this case is the line x equals negative 5. And then if I do it again, I'm then hitting the line y equals ln of x. All right, we'll get to that ln of x part second, but let's first set up my integral. I'm going to do pi times. Now think about this. My bounds are now going to be, the vertical bounds is going to be here and here. I'm going to go from 0 all the way up to 1.609. Okay, it's not going to be from 1 to 5 anymore, since it's going to be a vertical rotation. My outer radius, or the longer of the two lines I drew, is just 5 minus negative 1. It's going to be constant, but I'm still going to write it that way, 5 minus negative 1 squared, and then I'm going to subtract from it the inner radius, which is the second shorter line I drew. But since I'm doing this horizontally, I can't use the function y equals ln of x. I need to change it into x equals something. Now here's where some of you ln specialists might have excelled, and if you're not as comfortable with ln, this may be a little bit of a struggle. How do you get x alone in this case? How do you change into x equals something? If we do a simple log roll, e to the y equals x, I've now expressed it in terms of x. All we would then want to do is subtract out, e to the y represents the distance from the function to the x-axis. We need to go a little bit farther to negative 1, so we need to subtract a negative 1. So my inner radius would be e to the y minus -1 squared. And then this would be dy. Okay, a little bit tricky. Okay, definitely tricky to walk through, but hopefully this gives you some practice with the radius. All right, so for your homework or classwork, it's going to be problems. Let's see here. What should we do? Definitely problem 1. And let's do problems 1, 2, and 3. Most of them are just setting up integrals and not actually solving for them, so it can be a little bit quicker. But 1, 2, and 3 is for homework. I am going to actually do the solutions for number 1 on the video here. So hopefully, if you're struggling with a little bit of it, you certainly can follow along with my solutions here. The rest of the solutions will be on Canvas, but your homeworks are problems 1, 2, and 3. Pay careful attention to what problems say no calculator versus calculator, what problems say skip certain parts versus parts you can do now. So in problem number 1, you can skip part C. So your homework is problems 1, 2, and 3. I'm going to work through the solutions on part number 1 now, but I suggest you pause the video, try to do parts 1 and 2. Okay, do parts 1 and 2, and then hit play if you feel like you need some more explanation on how to walk through parts A and B. Again, we don't need to do part C. And the solutions will be on Canvas for all of them. But again, your homework's going to be 1, 2, and 3. So if you want to do part 1 or problem 1, hit pause and then hit play once you've gone as far as you can go, and you can walk through how I do this one. All right, so let's walk through problem number 1 here. So 1a, we have let f of x equal 2x squared minus 6x plus 4. G of x equals 4 cosine of 1/4 pi x. Let R be the region bounded by the graphs f and g as shown in the figure above. Part A is find the area of R. So no volume, we're going back to area. Area is top minus bottom when it's contained between two curves. Okay, 2x squared, you may be thinking, all right, well, which one is f, which one is g? Well, I know f of x, 2x squared, that's going to be a parabola shaped, and it's positive, it's going to be upward facing parabola. So that must mean the only possible one it could be would be this bottom one. So that must be f of x. And then cosine, we know, starts at a max. So that one might also make sense that that one, that with the downward shape that we can see, is g of x, okay? So if we're finding the area, it's as simple as top minus bottom. If you remember that, top minus bottom. My bounds, it looks like they gave us the points of intersection. So my bounds are just going to be from 0 to 2, okay, of g of x minus f of x. Okay, so g of x in this case is 4 cosine of 1/4 pi x minus, don't forget the parentheses, 2x squared minus 6x plus 4 dx. Now the integral of 4 cosine of 1/4 pi x, you could use substitution if you'd like, but actually the integral in this case is going to be as simple as taking the integral, leaving the inside the same, and normally you would multiply by the derivative of the inside to take the derivative, but to take the integral we're going to divide by the derivative of the inside. Again, you can use substitution if that doesn't make sense to you, but I'm going to shorten things up by just doing it using that quick method. So the integral of 4 cosine is going to be 4 sine. Inside stays the same, and then it's divided by the derivative of the inside, which is 1/4 pi. And again, if you don't believe me that the derivative of that would be 4 cosine of 1/4 pi x, just take the derivative of that, and you'll see that it does work out to the original one, so that must be the integral. And then if we take the integral of the second piece, just be careful, we have minus, maybe 2/3 x cubed minus 3x squared plus 4x, and we're evaluating all of this from 0 to 2. All right, if I plug in 2 for x in the 4 sine piece, I get 4 sine of pi over 4, 2 pi over 4, so pi over 2. Sine of pi over 2 is 4, so I get 4 over 1/4 pi. Then if I plug in 0, I get 0. or actually we don't even have to worry about that yet, but we'll get there. Minus, okay, I'm going to just distribute the negative 16 thirds minus 12, excuse me, plus 12 when I distribute, and then I plug in the 2, I get minus 8. And then we're going to subtract from it that entire thing, but I'm plugging in 0, but it's going to be 0 for all of them, so that's just as far as we're going to go. And so if I simplify this, I get 16 over pi minus, if I do all of that, I think it comes out to 4 thirds. So the area between the curves should be 16 over pi minus 4 thirds. Again, probably the toughest part is taking the integral of the 4 cosine piece. Again, if you're having trouble, do use substitution. You can certainly do it that method. Okay, for part B, it says write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated around about the horizontal line y equals 4. So I'm just going to draw on the line y equals 4, and let me actually, that's fine. There's the line y equals 4 right there. I'm rotating R around that. This to me is clearly a donut problem. Okay, it's a donut problem. Okay, so I know R is contained between the bounds 0 to 2. So that's easy. Now I just need to define my outer radius minus my inner radius. Okay, my outer radius, again, the way I'm going to do it is draw a line from the axis of rotation to the two functions. Okay, the longer one will be your outer radius, the shorter one will be your inner radius. So those two lines in blue. So how would you define the distance between the green line, okay, and this function f of x down here? How would you define, how would you define the distance between those two things, the line in green and f of x? Well, it would just be 4 minus f of x. Go back to red, or black, excuse me. 4 minus f of x. And since that's a radius, we need to square it. And then we're going to subtract our inner radius. How do we define the distance between the two functions, or that short line in blue? That's just going to be 4 minus g of x. 4 minus g of x squared. And that's dx of, there's part B right there. Now notice I didn't actually use the actual functions. I just wrote f of x and g of x, and you can do that, especially for these longer things. Since they're defined in the problem as f of x and g of x equals this, you can use f of x and g of x wherever you like. So that just makes it a little easier when you're setting up these problems, that you could make a careless error and put a negative where you mean to put a plus, or vice versa. So if you can leave it in terms of f of x and g of x, I would recommend you do that. All right, so that's A and B. C we can skip for now. And then the rest of your homework is to do problems 2 and 3.